In November 2025, research led by Harvard, including collaborators from MIT, QuEra, UMD, and NIST, published a landmark result in Nature. For the first time, every essential element of a fault-tolerant quantum computer was demonstrated together in a single working system. Not in theory, not in pieces, all of it working at once.
I would say with that, we really established very solid scientific foundation for the first time in history. And I should say that at this point, these kind of dreams and ideas, that many of us had for over 30 years, for the first time, they're really in direct sight.
We are truly on the cusp. We are a handful of years away from true quantum utility.
For decades, quantum computing has been a promise, a theoretical possibility that always seemed just out of reach. But something has changed.
About 2 years ago, where for the first time we actually started implementing complex algorithms with this protected logical qubits. By then, that was definitely the first time, anyone has ever been doing that. And it brings us to the moment today where we actually, again, for the first time, implemented and combined together all elements which require one to operate this kind of large utility scale, machine.
When we talk to executives, we show them that QuEra is both the scientific leader as well as the commercial leader in neutral atom quantum computing. For the scientific leadership, there's really no debate. You look at the volume and of our achievements together with our scientific partners, Harvard and MIT. You look at the demonstrations of large number of qubits, of logical qubits, of magic state distillation, of efficient algorithms. There's just no debate that we are the scientific leader.
I think this is a very special time in the history of quantum physics, quantum technology, and maybe technology more broadly. And we are here at a very special place where we're in a position to really, realize these ideas and dreams.
But reaching fault tolerance requires solving one fundamental problem: errors. Quantum systems are fragile, and without the ability to detect and correct errors, quantum computers can only run short, limited calculations.
In fact, error correction is really table stakes these days. If you don't have error correction, then you really shouldn't be in this market.
There's not an end line of quantum error correction. We will start to make the errors smaller and smaller, which means that you can run longer and longer circuits. If you have an error of 1 in a million, it means that you can run 1 million lines of code. This will be our first goal. As we push the errors smaller to, say, 1 in a billion, then you can run 1 billion lines of code.
QuEra's approach starts with a fundamental advantage: neutral atoms.
One of the things what attracted me to the neutral atoms, all the qubits are the same. There are no differences. And one thing which is also very interesting, we are building for each application an ASIC in the vacuum, using the atoms, organizing them into an application-specific integrated circuit.
With neutral atoms, you have this big advantage that they don't interact unless we turn on laser beams. So most of the times they don't interact, and so when we want to prepare the system, it's very, very easy for us to scale things up. We just need to scale up the number of laser beams that we use to trap the atoms.
This architecture has enabled QuEra and its research partners to achieve a series of error correction breakthroughs, each one a critical step toward fault tolerance.
Through a landmark demonstration in December 23, demonstration led by Harvard with QuEra and MIT and University of Maryland and NIST, we've shown that the answer is yes, you could detect and correct errors.
Quantum computers work with quantum gates, and there's 2 types of quantum gates. One that are somewhat easier to make, which are so-called Clifford gates, and ones that are also necessary for quantum computation that goes beyond classic computing, but that are not so easy to make. And so QuEra had recently a significant success in achieving those second type of gates. They're called magic state distillation, and this has been published in Nature, which is, the prime science outlet, peer-reviewed in the world.
what we are trying to do, it's kind of unprecedented. Now engineer systems, while at the same time still, pushing the frontier of basic science. This integrated approach is what really allows us to basically change the slope of the development, to accelerate the progress. In some cases by years, maybe even by decades. We know enough already now to start building systems, to start addressing applications.
In theoretical quantum error correction, people just assumed all errors are the same. In real systems, they are not all the same. And if you know which kind of error is dominant, you can, for instance, come up with theoretical concepts to write error correction codes and encodings of logical qubits that take advantage of this fact, and they scale much, much better than before.
Of course, any company can make claims. What matters is proof. Published, peer-reviewed, reproducible proof.
We have been exceptionally strong together with Harvard and MIT and our other academic partners. We've been exceptionally strong in the science. Without science, there's nothing. Without science, it's just PowerPoint. We are both excited about the potential of quantum, but we're both clear-eyed about the challenges.
The other core advantage is that we really publish our results, both QuEra and in that field. This is very, very valuable. So we are not siloed off, and we are exposing the results to the world to criticize, to analyze, and that's really, really crucial for progress.
This open approach, publishing results, inviting scrutiny, and building on verified science is what separates real progress from marketing claims.
We discovered how to do arbitrary gates and create architectures that had all-to-all connectivity. And these are really key steps to enabling universal computation. And the minute we realized how to do those things, and we were the first to get to that point, we became experts overnight in the programmability axis. We figured out how to confront the key challenge to scaling up, which is how do you replace the atoms that are lost continuously in a calculation?
The science is proven. The technology is advancing. The question now is, who will be ready when fault-tolerant quantum computing arrives? Partnering with QuEra can help forward-thinking organizations take the concrete steps needed today.
Let me give you an analogy. If you had to take a medical exam, a medical licensing exam tomorrow, I think it's likely that you will fail, even if you crammed all night. But if you had to take that exam in 2 or 3 years, and it was really important to you, then you can come up with a plan to make it happen. This is where quantum is. If you wait until quantum is ready to deliver commercial quantum advantage or commercial utility, then you're too late.
If you're scaling up a workforce development program and it involves a new PhD program, your timeline to impact on that is at a minimum 4 years. We're now to the point where that timeline compares pretty closely and favorably with what most people's expectations are for quantum utility.
The science has largely been worked out, and it becomes an engineering issue about how to construct a machine and wrap it in software and functionality so that people can use it. But it's going to happen, and it's going to happen quickly.
We are extremely well capitalized and liquid, so we absolutely have a very, very long cash runway and the capital needed to deliver on our roadmap and vision, and even to fund a go-to-market initiative. We're in great financial shape.
I have deep conviction that QuEra is the ideal and best partner for customers in this marketplace over the next 5 to 10 years. We are very focused on real science. We have the resources, the commitment. We'll continue to over-deliver on the things that we commit